Inversion formula for dilogarithms. So basically, I do think you know about dilogarithms now because like this is not the first video involving dilogarithms on my channel. So basically, I will link a playlist over here where I have introduced all of these functions, and so it will be easier for you to catch up with me. Okay, so now you know about dilogarithm functions. We will start the video. So basically, in this video, what we will do is we will try to use this uh, property from Leibniz rule. Basically, if we have integral from 0 to x and derivative with respect to x of f of x, then this is just f of x itself. So we will try to use this. So basically, what we will do is we will basically try to take the integral and then derivative of li2 of 1 by x, yeah, and we will get this thing to be minus li2 of x and then minus zeta of 2 minus 1 by 2, this blah 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 thing, yeah, and this is basically li2 of 1 by x, yeah. So that's why we'll prove this identity. So this is our flow of proof, and now let's see how do we do this. So first of all, let's try to differentiate the li2 of 1 by x. Yeah. So we know that the if we differentiate this, so basically we will get minus ln of 1 minus 1 by x by 1 by x. Yeah, basically derivative of li2 of something is just this thing. Now derivative of 1 by x is minus 1 by x squared dx. Yeah. Now minus cancels out and we have ln of 1 minus 1 by x by x dx. Now we can write this as ln of x minus 1 minus ln x by x dx. Now I shall change this to 1 minus x, and for that what I can do is I can just add plus ln of minus 1 on both sides, on both logs, and that will give me ln 1 minus x minus ln of minus x by x dx. Okay, now this is just the derivative of li2 of 1 by x, yeah. Now let us integrate both of them from 0 to g, yeah. Now this will just give me li2 of 1 by z from Leibniz rule, and over here we will have integral from 0 to g of ln 1 minus x by x minus ln of minus x by x dx. Okay, so now what else can we do? So basically we now know that if there is a minus sign over here, minus over here as well. Now this is just the definition of li2 yeah, for z. So we have minus li2 of g, and to integrate this we can just use the substitution. Basically I can write this as minus over x over here, and this is also d of minus x over here. So minus 1 from here and here cancels out, so I can write it like this. Now if this is y, 1 by minus x this one is just dy, yeah. So that's why it is like y dy basically. So I can write this as y square by 2, so 1 by 2 ln of minus x whole square, and this is from 0 to g, yeah. Is that okay? So from 0 to g. So basically we might be evaluate this you might be able to evaluate this at g, but at 0 like we won't be. So for that purpose how we can do this is basically this is minus ln 2 of g, and now we will write this as 1 by 2 ln square of minus c. And then since we don't know the other value, let us write this as plus c only. Yeah, now we know that this is li2 of 1 by g. Now to find the plus c, we also have an alternative way. Yeah, the alternative way is, now let us put g equals to minus 1 in this equation. So we get li2 of this is minus 1 is equals to minus li2 of minus 1, that is and minus 1 by 2 ln square of 1 plus c. Now ln of 1 is just 0. Yeah, so we have c is equals to 2 times li2 of minus 1. Yeah, now let's try to find 2 times li2 of minus 1. 2 times, the sum definition for li2 is sum from n equals to 1 to infinity, g is minus 1 to the power n by, now this is just n square. Now if here was n plus 1, this would have just have been eta of 2, but since we just have n, so this is minus eta of 2. Now we know that eta of 2 is just pi square by 12, so this is 2 times minus pi square by 12, so that's minus pi square by 6. Okay, so now we have the c as well, and so this problem is probably solved now, because now we can substitute c, and that gives me li2 of 1 by g is basically minus li2 of g minus 1 by 2 ln square minus g, and then this is minus pi square by 6. Yeah, take this to other side, and that gives us li2 of 1 by g plus li2 of g, this is actually equals to minus pi square by 6 minus 1 by 2 ln square minus g. And so we proved this result. Wasn't it the thing that needed to be proved? Let us check if this is what we need to prove. li2 of g plus li2 upon by g equals minus pi square by 6, which is zeta of 2 first here. Yeah, pi square 6 is just zeta of 2 minus zeta of 2 minus 1 by 2 ln square minus c. Yeah, so we proved the result. So basically over here, to prove this, we just differentiated this thing and also integrated this thing, and we got a different result for li2 of 1 by g. Yeah, basically we are trying to get the same thing but in a different way. That's why we got a new result for this function, and so this result came out to be like this, and that was what we wanted to find out. So basically, using this formula, we will be able to find li2 for any fractions using simpler terms. So basically this can be helpful for finding li2 of some fractions. Yeah, so hope you enjoyed the proof, and also I look forward to seeing you in my upcoming videos where I prove Landon's identity. Yeah, and if you are curious what Landon's identity is, so that is li2 of minus g plus li2 of g by 1 plus g. This is actually equals to minus 1 by 2 ln square g plus 1. Yeah, if you want its proof, let's check out my next video. And yeah, thanks for watching. Look forward to seeing you in the next video.